If you talk about water waves as being transverse, strictly speaking, you should talk about surface water waves. Some exams do, this one doesn't. It's just that you can get sound, of course, in water. And if sound is in water, it is not transverse, it is longitudinal. So a surface water wave if you're being absolutely fussy. So other examples of transverse waves, the best thing to do, I think, is to quote any electromagnetic wave. Radio, micro, infrared, any of those, the oscillations will be at right angles to the direction of wave propagation. And of course, the classic example of a longitudinal wave, you just simply say sound. And then in part 3, they ask you to distinguish, or rather to compare the motion of the particles. They do mention transverse and longitudinal. Both words are used. So if you're going to compare or distinguish, you describe both. Don't just say what a transverse wave is. So it's the usual thing. The oscillations of a transverse wave are perpendicular to the direction of propagation. The mark scheme did allow also the direction of energy transfer. Whereas with longitudinal, the oscillations, they are parallel. Part B then goes into a graph. Now these graphs, you can get a lot out of them. Maybe I'm going to go into a little bit too much detail with this one. This is a film because you've got displacement on the vertical axis, you always get that, but you've got time on the horizontal. So what's happening is you look at an individual particle, one particle, and ask, where is it as time goes on? And you can see with the graph that they give, it starts off with maximum displacement. So if I say, for example, it's this particle here that's oscillating up and down, and the wave, of course, would propagate to the right, but we're homing in on this individual particle. According to the graph, I'm starting filming it when it's at the top. So it starts here. And it's about to move vertically down. Of course, time's on the horizontal, but it's not going to the right. It's going vertically down. And the oscillation then carries on. A bit later on, they're going to ask you for a graph for something which is 90 degrees out of phase, which of course is a quarter of a cycle. And the particle that's been drawn starts there and is about to head down. If you want a quarter of a cycle lagging behind, then you would start your particle there. It hasn't got to the top yet. It starts there and then it'll get there a bit later on and then do what this particle is doing. Anyway, we'll have a little look at that a bit later on. In the diagram that they give you, all you've got to do is label with a capital A the amplitude. Now, I've gone for that orange double-headed arrow there. It's a very simple thing. They could have asked you that, of course, at GCSE. Part 2 then asks you for an accurate value for the period of the wave. Now, if they ask you for an accurate, there's been a lot of debate about the difference or the similarities between the word accurate and reliable. Anyway, this time it's accurate, and what that implies is you don't just look at one wave. In fact, it's going to be quite appropriate to use 3 waves. If you look very carefully at the graph, you'll find that the peaks don't sort of go exactly onto a very definite time interval. So, for example, even that peak there, I don't think it's absolutely on the 2-second mark. I think it's ever so slightly to the left. So it's not a very easy graph to look at, but we're going to take 3 waves. So we start there. I'm going to assume that the start of that wave is accurate, and then there's 1 wave, and 2, and then 3. I'm going to simply say that that takes 2 seconds to occur. So 3 oscillations in 2 seconds. That means the periodic time is 2/3, 0.67 seconds, and that's what they want you to give. I think 2 decimal places is completely valid, because if you look at the value in time of each small square, it's 0.05 seconds, and clearly that goes to a second decimal place. So it's 0, 0.05, 0.1, and so on. So two small squares are worth 0.1, 0.1, 0.2, 0.3, 0.4, 0.5, and so on. It then gives you the speed of the wave, 3.5 meters per second. What's the wavelength? Well, v is equal to f lambda. Everybody knows that equation, but how do you convert it into an equation with periodic time? Well, the frequency and the periodic time, of course, are related, as f is 1 over t. So you could easily just simply modify that from the word go and say it's the wavelength divided by the periodic time. The wavelength then is v times t. They give you the v, we've just worked out the lambda, and we've got, sorry, the periodic time, and then we've got 2.33 meters. That's the periodic time. And then lastly, in part 4, a wave of the same amplitude but 90 degrees out of phase. Now there are two versions of this. You can draw a wave that lags by a quarter of a cycle, or you can have a wave which leads by a quarter of a cycle. I've gone for one which lags simply because it was a little bit easier to draw. And going back to that little diagram we saw earlier, the particle they've gone for starts at the top. I'm going to start with a particle which starts there and is on its way up. It lags behind what that one does. That one's on its way down, this one's on its way up. And of course, if you start there, you would start with zero displacement there, and the particle is on its way up. So you can see that there's a time interval, that time interval there, a quarter of a cycle, which occurs before that particle there gets to the top. So the green wave, it lags behind the black wave that they've drawn. If it was going to lead and do everything before the black wave, then of course you'd have to have the wave displaced. I've displaced it to the right, you would have this displacement to the left, and that would of course be completely correct. I have drawn some plotted points. So when that's a peak, you get zero displacement. When the black wave is zero, then the green wave has gone to a peak, and so on. Worth plotting some points out just to get yourself nice and accurate. So a peak there and a zero there, and so on.